Okay, so today we're going to go over our first lecture or lesson over the mole. So basically a mole, you can just kind of, if it sounds odd to you, every time you speak about or think about the mole, kind of think about the word dozen. That might help. So if you look at the paper, you'll see that I have a dozen yellow balls. So a dozen yellow balls always represents 12, okay? So if I have a dozen of anything, that means I have 12 of whatever those things are. Whether that's actual objects, or let's say we could say that I have a dozen kilos of something, that would be 12 kilos of something. Or let's say I have a dozen liters of something, that would be 12 liters. So keep in mind that when we talk about the mole, it's just like a number, okay? Picture it as a number, a constant number that doesn't change. And that's what it is. It's actually a constant. So it's kind of like also thinking about a couple. If you have a couple of balls, okay, you have two balls. That's couple usually means two. So you have a couple of balls, that means two. If you have a couple of kilos, you have 2 kilos. If you have a couple of liters, it's 2 liters. So the mole is just a number, but a really, really big number that we use to associate, let's say we have mass of something and we can convert it to how many actual particles of that we have. So we're just going to go over the history of that today, and I'm going to kind of show you how to calculate the mole. Okay, so this is basically what I just said. I'm going to kind of skip over it because it is in units that is used in the US, and you guys really don't care about it. But again, if you have 2 pounds of bananas, you could use it as like a couple of pounds of bananas, and so that would be 2, okay? So basically what I'm trying to get at is we can use the mole to convert from count. So for example, I have 12 balls, or we could use as mass, I have 12 kilos, or we can use it as volume, 12 liters, okay? So we can relate the mole to each of those types of measurements. Now, a history of the mole, there is a number that we use to calculate the mole, okay? And that number has a name called Avogadro's number. And it's the same number every time, it doesn't change. But the history of it, this is the guy it's named after. So he kind of started this idea of counting particles within a certain amount. So he kind of started this idea. It was a theory. He said, well, if you have a specific volume of gas at a specific temperature and pressure, it's going to have the same number of atoms or molecules regardless. So for example, if you have a liter of oxygen, you should have the same number of molecules for every liter of that oxygen. Loschmidt, he kind of moved a little further, and he was able to calculate a number of particles in a given volume of gas. And then this guy actually used that number, and he was able to calculate the charge of an electron based on Avogadro's number. So he was able to use it and calculate the charge of an electron. So that's what this guy did. And the other one, this last one, he's actually the one who named Avogadro's number, and he proved it in his experiments multiple times, and then he came up with a more specific definition, and he actually won a Nobel Prize for it. So he said Avogadro's number is the number of molecules in exactly 32 grams of oxygen. So if you have 32 grams of oxygen, then he used it as like that's the standard. So like we have a standard for gold or a standard for mass. We have a standard for the number of particles or molecules that you'll see in 32 grams of oxygen. And then that was later changed a little bit. So instead of oxygen, we actually use the carbon-12 isotope. And then here's the actual definition of the mole. So it's basically the same one as his, except instead of oxygen, we're using carbon-12 isotope. Okay, so it's the amount of any substance that contains as many elementary entities as there are in 12 grams of pure carbon. And basically, in 12 grams of carbon, I'm about to show you the actual number of the mole. That's how many molecules are there. So again, the mole is used to, I'm going to move this. The mole is used to bridge, so for example, if we have grams, we can actually calculate how many molecules we have. And you will do this. Let's use Jai-Ho since he still hasn't come and cleaned up his mess. It's been a year and a half now. Half a year, whatever. Let's say, I'm just messing with him. Let's say we have all of this copper chloride, okay? So let's say we got its mass. So I know how many grams it is. I can actually calculate how many molecules of copper chloride that I have based on Avogadro's number. I can say, oh, there's so many molecules in here. So that's pretty cool. It bridges the gap between atomic world and our macroscopic world, the big world, okay? So this is the number that we're talking about. Okay, so we're actually going to use dimensional analysis to solve this problem. So basically, I like to use, do you remember at the very beginning of the school year, we had a known and an unknown, right? So our known, if you look at the PowerPoint, is 1.22 moles of sodium. Okay, and you can abbreviate to make the problem shorter. Okay, and our unknown, it's asking how many atoms. So we don't know how many atoms of sodium, okay? Remember, we always started with our unknown. I'm sorry, our known. So it's 1.22 moles of sodium. That's our known, okay? And then we do the multiply, okay? And we need to cancel out our known down here. So moles of sodium. Okay, and then up here is what we're trying to get to. So we are trying to get to atoms of sodium. Okay, so basically, just like the PowerPoint previous, okay, 1 mole, I'll write it here, 1 mole is equal to 6.02 times 10 to the 23rd particles. Okay, I'm just going to say particles to include everybody, particles, okay? So basically 1 mole is equal to this always, all right? Just like 1 dozen is equal to 12 things, 1 mole is equal to this many particles, okay? That's all we're doing is just a fancy conversion factor with just a big number. That's it, don't be scared of it. So here we have 1 mole, okay, so 1 mole, and then this is how many particles we have. I actually didn't save me enough room, sorry. So 6.02 times 10 to the 23rd is what I'm writing, okay? And then whatever our answer is, that's our answer. So how I type it in the calculator. So I just type in 1.22, okay, times, and then I have my parentheses, and I just do 6.02 times 10, and then to the 23rd, and then in this calculator I just push over, close parentheses, equals, okay? So my answer is, I don't know if you can see it, 7.3444 times 10 to the 23rd, okay? So the answer, 7.3444 times 10 to the 23rd. So this is the, I'm sorry, I didn't write my units. So the moles canceled, right? And so we're left with atoms of sodium. All right, so that's our answer, except we do need to check our significant figures. This is a constant, so we leave it alone. Okay, this is not. This is where we get our significant figures from. There are 3 significant figures. This is multiplication, so we're looking at significant figures, not numbers past the decimal. So we have 3 significant figures here, so we can only have 3 here. So it has to cut off here. First, we take a look at this to see if it'll round. It won't because it's less than 5. So the answer will be 7.34 times 10 to the 23rd atoms of sodium. So that's our answer. All right, so next question is how many moles are equal to this many molecules of carbon monoxide? So carbon monoxide is what we're talking about. So our known, okay, our known and an unknown. We have a known and an unknown. So basically this tells us where we are and where we're going. So what we have is 4.79 times 10 to the 24. We get this number from the question. It always will tell us what we have. Molecules. I wouldn't abbreviate molecules just yet, or maybe abbreviate it to the C. That way you don't get it confused with moles, because later we will be doing moles, and moles is usually abbreviated with MOL. So I don't want you to abbreviate it MOL or MOLE because of the mole. So we have molecules of carbon monoxide. And then our unknown, it's asking how many moles are equal. So we do not know the number of moles of carbon monoxide, okay? So we always start with our known on our equation, which is 4.79 times 10 to the 24th molecules of carbon monoxide, okay? And then we have whatever is down here, moles. I'm sorry, that's molecules. See, I already did it, what I told you not to do. I have already confused my own self. Let me get white out. Okay. Molecules. Molecules, I can't spell. Okay, molecules of CO, okay? And then up here is where we're trying to get to, which is moles of carbon monoxide, okay? So now all we're doing is doing a conversion factor. So remember that our constant or conversion factor equals, it's 1 mole equals 6.02 times 10 to the 23rd particles. Okay, so that's what we do here. We have 1 mole of it. For every 1 mole of it, we have, again, I did not leave myself space, times 10 to the 23rd molecules of carbon monoxide. So now all you have to do is plug in the numbers. So you have, remember, anything with 1, you just ignore it. So if it's, you have a number here and a number other than 1 here, just take this divided by this. 8, blah, blah, blah. Okay, so we have that many moles of carbon monoxide. This is our answer. However, we do need to take into consideration significant figures. Again, this is a constant, so we don't really, we consider those infinite. This is not, however. We don't really look at this for significant figures. We're looking at this. Since we're multiplying or dividing, significant figures is what we count, not digits past the decimal. So we have 3 significant figures here. 1, 2, 3 here, so it needs to be cut off here. We're going to take a look at this number real quick to see if it'll round this up. It does. It is 5 or greater. So the actual answer is 7.96 moles of carbon monoxide.